potentially simultaneously transmitting with the source, and therefore there's a superposition of the signals you received. Okay? So, all right, so let's see if we can make some headway using this deterministic model to see what's going on. So the first question is, what is the Cutset bound? Right, the only game in town, so let's use the Cutset bound here. Cutset bound for this channel is very easy to calculate. Good. So the good thing about deterministic channel is you make yourself feel good. You're like, you're doing things. Whether or not it leads to anywhere, it doesn't matter. You're doing things, you're calculating, and you're getting numbers, and it's good. I don't want to lose students to, too many students, so I got to get students doing things. So the Cutset bound here, there are two of them. Okay? So a Cutset bound means what? Reminder, theorem 14.10.1 says that you do a partition. A Cutset, by definition, is a partition between the source and a subset of nodes contain the source, and a subset of nodes contain destination. And you look at the information flow between the source, between the left-hand nodes to the right-hand node. Okay? So in this case, we have two cuts, one cut here and one cut here. This cut is essentially a cut which tells you what's the maximum rate of information you can flow through this cut. And that is clearly given by the maximum of NSR and NSD. It's not LSD, it's NSD. My English is not very good. I have a bit of accent, so NSD. Okay. NSR is the number of levels from the source to the relay. So the maximum of that is the total maximum number of levels you can go through this cut, and that is just the information flowing through this edge. Okay. Similarly, the maximum of these two numbers is information flowing from this side to this side. So the maximum of the two, the minimum of the two is the minimum cut. Okay? So that's the Cutset bound. The question is, can we achieve it on a deterministic channel? And if so, how does the strategy look like? Now, we can rewrite this like this. I take out the common term, NSD, and I leave the remaining NSR minus NSD and NRD minus NSD plus. Okay? So this formula tells us the following, very simple. When the number of levels, NSR, is less than NSD, or NRD is less than NSD, then the relay is useless. You might as well just send information directly and forget about the relay. The relay is too weak. The pipes are too narrow for them to help out. However, if both NSR and NSD is greater than the two and the direct link, then the relays start becoming useful. The relay can carry, potentially, at least in the Cutset bound, potentially carry this extra information. Let's see how we can actually achieve it. Okay? So this is NSD, the blue. All right? So now there's one extra level here, and there's one extra level here, because these two levels cannot be used anymore. Right? So this is precisely this number. And so you can send that extra bit going below, and send that one extra bit going above, and you can convey this information, this one extra bit. Yeah?
So in the regular Cutset bounds, you sort of get MIMO bound, right?
Yeah, these are MIMO bounds, yes.
So in some sense, when you take a max of these two, so how are you losing the MIMO advantage?
No. Max of the two is precisely, essentially a maximum ratio combining type bound, right? When you say maximum ratio combined, you're adding signals together. Remember, in the language here, adding signals together is like taking the maximum of the two signals. So it's a maximum of the two. So these are precisely MIMO bounds. MIMO bounds. Okay. So, all right. So we have one extra bit. And so in this example, and in general, actually, for a single relay, we can achieve the Cutset bound like this. Okay, now the Cutset bound is achievable. Can we interpret this strategy? Can we interpret this strategy in a language that we know? In other words, in the list of array of strategies that I talked about earlier. Yes?
Maybe a trivial question, but when you had the second Cutset, was it not NSD plus 1 bit from the NRD? Why was it max of NSD?
You're talking about this cut.
Yeah.
The total number of levels that's received at a destination is equal to the maximum of the two, right? So you cannot get more bits than the number of levels you receive here. That's the maximum number of bits you can get.
So that's NSD plus 1 from NRD.
Yeah, NSD plus 1 in this example is NRD. But this is just an example. So, right, if you look at the number of levels here, what is it? It is the maximum of the number of levels received from the source with the number of levels received from the destination. That one is just extraneous in this example. Sorry, this 1 bit has nothing to do with the 1 bit gap and so forth. Yeah? Don't confuse yourself. Don't confuse me. So this could be like 3 or 4 bits, right? I mean, this is just an example here. Okay. All right. So now, all right. So question time, interaction. Question time. Can we interpret this strategy as one of those strategies that covert Algebraic and covert Algebraic tells us? Is it partial decoding forward or is it decoding forward? It's decoding forward, right? The relay, so the message is what? The message is 3 bits, right? The relay actually have access to all those 3 bits. So it's actually a decoding forward strategy. Okay? So decoding forward is optimal. So, well, this suggests, why don't we use decoding forward on this channel and see what the gap is. Now, this gap is not like earth-shaking calculation. Because the Cutset band is already there. Decoding forward you can explicitly compute. So it's just a matter of algebra. Okay? But in fact, what is interesting, which I don't know anyone have observed, it's not that difficult. The gap is actually a constant gap, 1 bit. At most 1 bit. And in fact, if you actually go and plot this gap as a function of the channel gains, you will see this kind of picture. The gap is 1 bit only for a small range, small range of parameters. Most of the time, actually, the gap is much less than 1 bit. Okay? So actually, decoding forward is actually a very good strategy on the relay channel. Yes?
So when you say decode forward, do you enforce the relay to decode the message also?
Yes.
So if h large, let's say, is 0, the decode forward is...
Yeah, then you decode...
0, right?
Yeah, then okay, that's a good question. I guess decode and forward. I see. So when I see, okay, so I think this is the case when the direct links is weaker than the 2 cross link, probably. Because what you can show is the strategy you would do is the following, right? If one of the cross links, if one of the relay links is weaker than direct link, you just use the direct transmission. As long as both of them are larger, then you start using the decoding forward. I think that is the strategy that will give you one bit gap. Yeah. Okay. Good. All right. So let's look at 2 relay. So here we have the famous diamond network. So no direct source destination link. in this example only. 2 relays. We can build a deterministic channel by now familiar. All right? By now familiar. Now, the Cutset bound is given by now 4 numbers. 1 cut, 1 cut, and so we have, we have this cut, which is the cut from the source. This cut, which is a cut going into the destination. This cut, which is the parallel link here. And this cut, which is this parallel link here. Okay? So you do the calculation. We did the calculation. And it turns out that, again, you can achieve this Cutset bound. And here's an example. Okay? So first, I broadcast the signal to the 2 receiver. Okay? And I broadcast it by breaking up the information into two messages. The green message is decoded at relay 2, intended for relay 2. The blue message is intended for relay 1. Okay, so broadcast. Now, relay 1 decodes this message and forward it, which precludes the use of this link. And relay 2 forward the message it receives and decode this. Okay? All right, so this strategy is partial decoding forward. So this is not decoding forward, because relay 2 actually cannot decode all the bits sent from the source. Relay 1 can, but relay 2 cannot. Okay? And you can now implement this strategy in the Gaussian case by looking at this as a broadcast channel and this as a multiple access channel. And you want to split your information rate in such a way that R1, R2 is in the broadcast and R1, R2 is in the MAC, which is a mimic of this. You maximize it, and then you can show that the gap is no more than 2 bits from the Cutset bound. And this is some random distribution on these gains, and this shows the histogram of how much this gap is, from how much fraction of the channel realization has a certain number of gaps. So again, you can see that again, most of the time it seems that the gap is very small, but the worst case is 2 bit. So partial decoding forward is near optimal. So far so good. Covert and Algebraic is working for us. The strategy is good. Now, let's look at a third example. Now, this example is more complicated. Okay. Now, this example has 6 nodes, 2 layers, 2 stages of relays. Okay. And I can build, again, a deterministic channel. I can build a deterministic channel. Now, let's look at this situation and ask ourselves, is decode and forward optimal? Is partial decode forward optimal to achieve this deterministic capacity? So let's look at the flow of information here. Can we take 5 more minutes? I'll finish this example, and then we're done. And we'll go for lunch. It's hard to fight with lunch, so I won't try that. So here's how the flow of information works. And this strategy achieves the Cutset bound. So first, you send the blue and the red are the bits you want to send. So here I'm achieving a rate of 5. Red is going here. Blue is going here. This guy is forwarding the blue. This guy is forwarding the red. Okay? Now, at this point, however, so far, information is still discrete. In other words, red and blue is still separated. Therefore, so far we've been doing partial decoding forward, essentially. Okay? We're decoding part of the message and forwarding it. However, at this point, the red and blue is merging here. Okay? And so the relay here actually cannot decode either the red message nor the blue message. So actually partial decoding forward is not working for us here. Okay? But what the relay can do is it can forward the modulo 2 sum of the signal. And this is the purple. So the purple is the merging of the red and the blue. Now what does the purple do for you at the final destination? Well, let's look at what the final destination finally receives. The final destination actually receives the 2 blue here and the 1 red here and the 2 purple here. Can it get these 2 reds? Yes, because it can now solve the equation, right? There are enough equations from the purple and from the blue to solve for these 2 reds. So actually, to achieve this particular strategy cannot be mapped into a partial decoding forward strategy. Okay? Now, the question though, so at relay B1, recap, the 2 LSBs are forwarded, the purple. So B1 does not do any decoding or partial decoding of the message. Okay, so now the question is, can this be implemented as a compress and forward strategy? So I went and read Gerhardt's paper on compress and forward, and I was like banging my head trying to read these formulas. Sorry?
You're probably confused.
Rather confused, I must say. But at the end of the day, our conclusion, tentative conclusion, was no, if you choose the auxiliary random variables to be Gaussian. Okay? Now, why is that? Let me see if I can figure that out. So this is done at like 2 a.m. yesterday morning. And so let me see if I'm still sane about that. Okay, so what's going on here? So suppose I say I want to do compressed and forward this signal, right? Because I'm not decoding. So the only choice I have, if I want to use covering the Algebraic scheme or the generalization of Gerhardt, is to do compress and forward this. If I do a Gaussian compress and forward, what am I doing? Essentially, I am saying that I want to quantize this receive signal and forward that. Okay? However, actually, quantizing means what? Quantizing in the Gaussian sense essentially means that it should forward the most significant bits. But here, I'm not interested in forwarding the most significant bits, because this red is already seen here. So I'm only interested in forwarding these least significant bits. So by doing compressed and forward, I'm missing out those 2 bits. And therefore, my conjecture is that Gaussian compressed and forward cannot achieve this performance either. However, that doesn't mean that you cannot use another auxiliary variable which is not Gaussian. But that would be quite difficult, because then you're looking at optimization over a very large space to find out what that is. Yeah?
But then if you use sort of like Wiener's, then you need to consider also the blue bits that going from the other direction. So does that not mean similar? Or?
The problem with Wiener's diff or any sign information is at the end you are only sending MSBs, most significant bits, because you're quantizing signal at both B1 and B2, and so whatever you're doing, you're sending MSBs of them. But if you look at this setup, I need to send LSBs of the 2 signals, and so I believe that compress and forward using Gaussian would not get the performance that we want.
Yeah, that's actually a good point. I'm not so sure. It's not clear to me. That's a good point, I think. It's not obvious.
The point being what, though?
Well, the point being that the top red, which is your MSB on B1, node B1, the top red, right, that's your MSB, your most significant bit. And you're saying that's what you send with compress and forward, but as the person pointed out, that red bit is available at the destination. So it's known, and when you do your binning, you're conditioning on that MSB, or with Wiener's if decoding. So it's not clear to me, and I think I see your point, but I'm not sure, given the comment, I think I'm not.
Yeah, so that's when I was struggling with the calculation midnight last night. So the problem here is that this bit, I understand, is correlated with this bit, right?
It's even known at the destination.
Yes, but this bit, if you think about these 2 as jointly Gaussian random variable, the correlation is at the LSB, so it's a very weak correlation. So
the destination knows it.
Yeah, the destination knows it in this model, though. But now I'm thinking about mapping this back to the Gaussian world, right? So now I'm thinking of Wiener's diff as these 2 are correlated Gaussian random variable. But since the correlation is with the LSB here, the correlation is very weak. And I'm not sure whether Wiener's diff would save me enough bits to do this. So anyway. At that point of confusion, yes?
Yeah, I don't understand how you map the arrows to LSB or MSB. It's like there are 3 arrows. You map them to lower 3 significant bits between A1 and B1. So we could map even at a higher level. And how do you choose what to map to?
This is the function of a channel, right? So this is an example of, so you give me a Gaussian channel, I map it to a deterministic channel. This is an example, right? So this mapping is a function of how many levels there are in this link. In other words, how strong this channel gain is. This is a specific example.
Collision may happen at MSB also, right?
Sure. But when collision, yeah. fine. No. Other configurations may happen in which compress and forward is okay. But I'm just trying to discuss whether this situation can be implemented by compress and forward. That's all.
At a different point, why would you consider this as compress and forward? It looks more to me like being the network coding kind of setup, that node B1 where you do sort of this.
That's right. That's what I'm leading into. Yeah, but what I'm trying to say is using this picture, and I want to say something about the Gaussian world, right? Because network coding is not in the Gaussian world, right? In the Gaussian world, they're always compressing forward, decoding forward, and partial decoding forward. Okay, so at this point we have examples, and we'll go for lunch, and then after the lunch, I will give you some general results regarding these. I was trying to figure out, that's why I stayed up so late.
Get you unhooked.
Oh, can start? Okay. Okay. All right. I should have to look at the time here. Control the time a bit better. There's no clock in this whole room. Okay, good. Let's start. Lecturing after lunch is a challenge. I have to fight with your pasta and salad. And that's hard. That's hard. Okay, so let's try to finish the relay network section, and then probably won't be able to get to scaling law today. I'll have it with a slide so you can take a look at it. But I would like to be a little bit slow here. First is after lunch. Second, I'm hoping for more interaction like we had this morning. It's good, I think. I'm taking the cue from Gerhard here. So good. All right. Okay. So, oops, what happened here? Oh, forgot this. So there was some heated discussion over lunch about various aspects of this example that are brought up. So I think the lesson we learned from this example is that if you think about the problem in a deterministic model, then your focus is shifted from looking at Gaussian random variables to a problem of transporting the bits and the stuff you receive at each level as a separate entity, as opposed to thinking of the whole thing as a received signal as a Gaussian random variable. And I think that's somewhat valuable. And in some sense, if you look at this model, this is now getting closer and closer to what? Closer and closer to network coding. That's right. So day 1 and day 2 is now merging. Very good. Consummating the union. Okay. I didn't say that. Mary is not here now. So, okay. All right. So that's right. So here's the question we're going to ask. Okay. Is the Cutset bound always achieved on arbitrary networks for the deterministic model? So we show some examples, 1-stage, 2-stage, diamond network, etc. And in all cases, actually, we can show that the Cutset bound on the deterministic channel can be achieved. And we'll show that indeed that's true. And the proof is actually borrows a lot of interesting ideas from network coding. So it's good now we can get a review of what happened yesterday. It's a little bit unfortunate because I don't know what happened yesterday. But maybe Gerhard or you guys can help me here. Sorry? I'm sure a lot of good things, but the question is, what can I draw on here? So did Muriel go through Raymond Young's proof, for example? Or no? Okay. All right. Okay. So I will do that, I guess. So we proved the answer is positive. Yes, it is true. Second, what is the structure of the capacity achieving strategy, and we'll give a structure here, and we'll try to follow the lead on the interference channel, and we will mimic this strategy on the deterministic channel to find an approximately optimal strategy for a general Gaussian network. Okay, and these are 3 things I want to understand this afternoon. So to do that, let's try to put more formal notation into our model. So this is the deterministic channel. In response to audience requirement, audience request, here there is a direct link from the source to the destination. Yes. Here the source can actually talk to the destination directly. And so if you look at the receive signal, okay, at a particular node, what is the receive signal at a particular node? It is a vector of bits. Each of these bubbles is a 0 or 1 output. Okay, so the receive signal is a linear transformation. What is it? It's a linear transformation on the input. And in fact, the linear transformation is specific. So if you look at this equation, the receive signal at node B1 is B1, B2, B3 shifted downwards, received at the LSBs, plus C1, C2, which is received from node A2, modulo 2, sum of these 2 vectors. So this is equal to, you can write it in matrix form. This is a shift matrix where everything is shifted down by 2. So it's a S squared. So 5 is the total number of levels. 3 is the number of levels you see. The difference is the amount of shifts. So each of the receive signal is a superposition of the shifted signal of the transmit signal from each of the signal of each of the transmitter, A1, A2, direct sum of each, modulo 2 sum between them. Okay, so this is the model. So algebraically, what's happening here is that in general, the receive signal at a particular time t, at a particular node j, is the sum of all the nodes that can reach that receiver times the shift of xit, where the shift is equal to q, the total number of bits, minus the number of bits that you can see. So n, the larger n is the, what is n? What does n represent? The stronger the signal, right? The larger n is, that means the more bits you can see from that transmitter, and therefore the stronger the channel. And the less shifting downwards you see. So that's why it's q minus nij. Okay? Where q, you can just take to be the maximum of all the nij across the network. S is a shift matrix. Every shift shifted down by 1 level. And all operations are on the finite field. Binary finite field. Binary field. Yes?
So are you saying more the number of shifts, the more signal is degraded?
That's right. That's right. Why? So look at this picture. B1, B2, B3, B4, B5. Yes? If this channel is the strongest, that means all 5 bits are seen here. If you shift down by 1 level, that means you only see 4 bits. If you shift down by 2 levels, you see 3 bits, and so forth. So the more shifting downwards, the more degradation, the more attenuation there is a channel, the fewer bits you see.
But doesn't it depend on the channel transfer function? Suppose there is no attenuation in channel and you don't have any interference.
Okay, so let's see what's happening here. Remember, okay, this is good. Each point-to-point link is measured by the number of bits you see here, right? The receiver. What I'm just trying to say is that this transformation can be written as a shift transformation, where the more shift you have, the less bits you see. Okay, it's okay, yeah? The interference is coming from the superposition of the signals. The summation here is a modulo 2 summation, is the interference. Okay? All right. So people are comfortable with this model. The structure of this model that is important to prove our result is the following. And actually, it turns out to prove the result we need, the shift structure is not so important. What is important is that the channel from I to j is represented by some matrix Gij. So here we have the received signal is a linear superposition of a transformation Gij from node j to receiver I. Okay? And G can be some arbitrary matrix operating on the finite field, operating on a vector space of dimension q over a binary finite field. Okay? All right. So if you look at this model, okay, then actually this model encompasses both our deterministic model, in which case the transformation is a shift matrix, and it also encompasses the Y-line network. Okay? So the Y-line network is nothing but a special case of this, where the Gij, okay, is such that there's never any interference at the receiver. So in a Y-line network, what you receive is directly the packets that you sent, or the bits you sent, at the various transmitter. So it's just a trivial linear transformation. It is a linear transformation, and you can put it in this form. So what I want to emphasize is that this general model it has a deterministic model for modeling the Gaussian channel as a special case, and also our standard Y-line model as a special case. People okay with that? Okay. So the Y-line model differs from the deterministic model in a case that there is essentially the main difference is that there is no interference at the receiver. In other words, when you send two symbols from two senders, they are all observed independently on two dimensions at the receiver. So you can receive both packets separately. Whereas in the wireless channel, some of those bits are received separately, and some are interfering with each other. Okay? All right. Okay, so as usual, we start with the upper bound, which is the only game in town. So do it more carefully. The upper bound is a partition, a cut, omega, is a partition of the nodes, the network, between the source nodes, the nodes on the left, which include the source and some subset of relay nodes, and the complement, which is the destination node and some other relay nodes. There's a partition. Now, what is the Cutset upper bound? The Cutset upper bound is essentially thinking of the left-hand nodes as forming a gigantic multiple antenna, shall we say, transmitter, where the transmitter is grouping together all the nodes, and a multiple antenna receiver, where the receiver is grouping all the nodes, and calculating the mutual information between the input and the output, conditional, very important, conditional on the input, the signal you send on the right-hand side. Okay, so this is theorem, thank you, 14.10.1 in Coburn-Thomas. By the way, they have a second edition now, right? So it's probably not the same number, right? Okay. All right. Okay. Now, this is the Cutset bound, and let's look at what it is, review of Chapter 14 of Coburn-Thomas. You first fix an input distribution, okay, which is a joint distribution over all the input that you send at each of the nodes. And then for that input distribution, you minimize over all the cut and compute the mutual information. And then you maximize over all input distribution to get the best achievable performance, the Cutset band. Sorry, not the best achievable, best Cutset band. Yeah.
So for the upper band, you allow cooperation between the nodes?
Yes, yes. So, yeah, it's, so the two things amazing about this bound, if you can achieve it. One is the fact that you're optimizing over all input distribution means that you can allow arbitrary coordination between these nodes, as though they are all controlled by a central transmitter, central source. Yeah. Two, the fact that you're conditioning means that somehow you are able to remove this message. Okay? You're able to remove the message you transmit on the right-hand side. Okay? None of this is a priori clear that is achievable. Okay? So this is the Cutset bound. In any case, it's the upper bound. Okay? Now, for our network, for our linear finite field model, so now we're focusing on our linear finite field model. We can compute this bound. So it turns out that this Cutset bound can be computed very explicitly in our model. And the Cutset bound, C bar, is just simply given by the minimum of the rank of the matrix G from omega to omega complement. Now, what does this G mean? Remember that each of the system here is given by a matrix, right? So if you club all these nodes together to form a big vector, and you club all these nodes together to form a big transmit vector, you can connect these transmit and receive vectors through a gigantic matrix, which is formed by essentially putting all these Gij together in the appropriate place. Yeah, so block form. Okay? So you get now a big gigantic matrix, which is your G. And that's what I call G from omega to omega complement. Okay? Now, at the output, you don't consider any of the transmit signal here, and that's incorporating this conditioning. So I claim that this Cutset bound is equal to this value. Now, this is a vast simplification from this. Number one, there's no maximization anymore of the input distribution. Number two, the mutual information can actually be computed very easily. Now, why is that? And here lies, again, what I said this morning, the simplicity of the finite field model. So this is essentially a very similar reason why in the Algebraic and Costa deterministic channel, when I apply to the deterministic finite field channel that we have, we can compute the capacity very explicitly. It is because that since we're dealing with a finite field, okay, the mutual information here, since we're dealing with a deterministic channel, the mutual information here is actually equal to what? All right. Can anyone tell me what the mutual information is? This is equal to the entropy of the output given the omega complement, right? Minus the entropy of the output given x omega and x omega complement. Let's write that down. Okay? Now, this together is all the inputs in the whole system. So therefore, given all the inputs in the system, the entropy of the output is 0 because we have a deterministic channel. So we get this. So therefore, to maximize this, all I need to do is to maximize the entropy, okay, of the output given the input on the right-hand side. But this entropy is always less than the cardinality of the range space of y, the possible values that y can take on given this. But this is less than log the rank of the transformation G from omega to omega complement. Okay? Because G times omega complement, the range space of this mapping, the number of values there gives what y can lie on. And so the log of that is the dimension of that space, which is the rank of the space. So therefore, this number is always less than or equal to this number, no matter what the input distribution is. Okay? And by choosing a specific input distribution, you can actually simultaneously achieve that. And that input distribution is uniform. If the input is uniform input distribution, then the output is also uniform in the range space. Not uniform over all possible output, of course, but uniform over the range space of G. Okay? And that's the beauty of the finite field model, which is in some sense a special case of a channel called, a class of channel called symmetric channels. If you look at Gallagher's book, I don't know how many people actually look at Gallagher's book anymore, but actually in his book, he actually used a lot of examples from this class of symmetric channels, where he showed that the input, for symmetric channels, the input is always uniform. The optimal input and optimal input is always uniform. And this is a special case of that. So we're using that structure. Yes?
So actually, you're saying the uniform is also optimal for the conditional case. Maybe that's true because it's a linear?
Yes, that's right. That's right. We're using linear property here. Because condition on this, the output can only lie in the range space of this, because this function only looks at the input from the left-hand side and right-hand side, freezing the input on the right-hand side already. Yeah. Okay, good. So linearity, finite field is used fully here in computing this. So good. We have a nice expression for this Cutset bound, and now the theorem is that this Cutset bound is actually achievable. Okay. In other words, the capacity of the deterministic channel, of the relay deterministic channel, is equal to this Cutset bound, which is given by the minimum of or the cut of the rank of this function. Okay. Now, let's see what this minimum of omega, the rank of g omega stars. Okay. So what is this rank in the y-line case? So if you think about rank, the rank tells you the dimension of the output, right? In the y-line model, the dimension of the output is simply the number of unit capacity link which can cross that cut. That's the dimension of that space, because everything is independent anyway, no interference. So therefore, the rank is just a summation of the capacity of the link from omega to omega complement, from omega to omega complement. Okay. So therefore, this number is actually the min cut of a standard min cut of a y-line graph. Okay. So therefore, you can think of this theorem as really a generalization of the famous Ford-Fulkerson theorem, which says that the maximum flow from the source to the destination is equal to the minimum cut, where a cut is defined as the total number of unit capacity lengths that cross that cut. Okay, and this is the Ford-Fulkerson theorem. So this is a natural generalization of that to the class of channels where each transmitter receiver is connected by linear finite field transformation. Okay, all right. By the way, since we talked about network coding yesterday, let me just connect a little bit to that. You can push this result further, okay? And you can also show that you can push a general result for the multicast scenario. So as we heard yesterday, I'm just imagining what you heard yesterday, that if you send information from the source, same information to multiple destinations, that's called a multicast problem, then this answer, the capacity is the maximum rate you can flow to all the nodes simultaneously, and is given by the minimum of all these cuts from each source to all the destinations, and that you can also achieve, turns out. Okay, but that will become obvious why as we go through the proof, because our proof is somewhat similar, with a very important difference, which I'll focus on. Okay, now comes the proof. So for a special case, let's first consider the situation where the network is staged. Staged means that there is no direct link from the source. So as you notice, the source destination link again disappears. It turns out to be important. So that's why when you asked me earlier, I said it turns out to be important. So it turns out to be important that it isn't there. And in fact, the general property that we want is the following. We want the path of the length of all paths from source destination to be the same. Okay? That means if you look at all the possible paths from the source destination, they're all the same. In this example, 1, 2, 3. All path 3, length 3 paths. And that implies that the length of all paths from source to any node, in fact, is the same. That's just equivalent, of course. Okay, and this is the definition of a staged network. And it turns out that for a staged network, things become simpler. Things become simpler. And here's why. Suppose I want to send a message, okay? I want to send a message, M1. And now each node, the source node, will do something. And then the next message flow in. Now the source node is done with M1. And now it encodes M2. And while it encodes M2, okay, the node in the first layer, so once you have this property, then you can define the nodes into different layers, where each layer corresponds to how many hops it is from the source. So when the source encodes M2, the relays will be all encoding M1, and so forth. And M3 will be encoded as source, and M2 will be encoded at A1, and M1 will be, whatever function of M1 will be further encoded at the relays. Okay? So the good thing about this staged network is that messages never catch up with each other. So there will never be a case in which if you operate in a block mode, each message comes in, you map it into a block, and you send it off. It will never be the case in which at any time a node will receive signals that are a function of two different messages. Why? Because it takes exactly the same amount of time for each message to propagate through the network. Okay? Now that turns out to be quite important. And that's why we needed to throw away this source destination link. For example, if I have a source destination link, then in one go, M3 will propagate to D already, and that will mix up with signals you receive from, say, M1. That's no, okay? So if you are a communication person, this property of equal path is essential for me to avoid. Avoid what? No, if you're a communication person, like hardcore, like modem designers, you know. ISI, right? There's an ISI. This is exactly an ISI phenomenon, right? An inter-symbol interference is one in which signals from earlier symbols, in this case earlier message, get caught up and interfere with the current symbols. And that's the analogy here. So to make this assumption, I first avoid the ISI problem. No ISI problem. And now I prove. Now I try to prove a result for that. Now, network coding people, wireline people, they don't really have to worry about this issue so much. Why? Because in wireline, you receive symbols separately across your links. So they never mix up. So you may have, it really doesn't matter too much on when you receive them. You just have to collect all of them and make some decision. Here I have interference. Because I have interference, nature is forcing signals to receive at the same time. So I can't really separate out them. Nature is forcing it just on me. So I need to make this assumption to make my problem easier first, and then move on to solve the ISI case. Okay, so, and then the decoder can decode each of the messages separately. So now the problem is decoupled, and I only need to focus about the first message. I don't have to focus about the interaction between different messages. Okay. Now, this discussion, so we had like a 1 hour discussion on this strategy over lunch. And so good, now it's fresh on my mind. Okay, so it turns out that one can use the network coding founder's basic result, okay, which is a paper by Algebraic, Kai, Young, and Lee, or some ordering thereof. Algebraic, Kai, Lee, and Young, right? ACLY. Yeah, ACLY paper. And when I gave this talk at the Chinese University, where A and L are, or L and Y are, they were quite happy. They were quite happy. They said, you know what? I don't know if anyone has read that paper. It's not the easiest paper to read, but it has good stuff. Good stuff. And in fact, the proof actually, you know, if you think about network coding, there are sort of two developments. One is deterministic, sort of try to construct linear transformation, and two is random, which is served to randomly code. In fact, the original paper is already random. It's already random, okay? And so what does it do? Okay. So first, it maps each message into a random code word of length t symbol time. By random code word, I mean you take the message, and for each of the message, you choose a completely random dimension t vector from your output symbol. So in this example, the output symbol at each time is basically a vector of dimension 5. You just pick something completely random and uniformly from that vector at each time, independent across time for t time. And that's the code word you ship out. Okay? So that's a random coding strategy. Each relay takes the received signal and again randomly map the received signal into a transmit code word. So every relay is completely random and independent of each other, maps the transmitted code word of dimension t, again completely randomly, uniformly chosen from the output space. From the input space, I should say, from the input space, because it's sending it forward. Okay? Now, and it turns out that this strategy, so what's happening here is essentially now at the receiver, okay, the receiver receives a received signal, which it collects from the signals transmitted. Okay? From the received signal, it's trying to figure out the transmitted message. Okay? It can decode correctly if there is a unique message which corresponds to that received vector. If there are two messages, it's screwed. It doesn't know what to do. Now, remember, there's no noise in this problem. So everything is, the encoding is randomly chosen, but once randomly chosen is fixed, so the decoder, of course, knows that. And so if there are two possible messages which map to the one received vector, then it cannot decide. Okay? And so the error event is essentially error event when two messages get mapped into one guy. Okay? So we can analyze that. It turns out that you can show that the min cut is achieved. Now this proof is actually quite similar to Raymond Young's proof, or ACLY proof. But let me say a few words there too, since Muriel didn't talk about it yesterday. Okay? So the error analysis, actually the error analysis is clearly done by an information theorist. I mean, it's a hardcore information theory proof. And in fact, it's actually not totally different from proof in the 70s about multiple access channel. So in a multiple access channel, you basically have to worry about a lot of pairwise error event. So the trick here to analyze this is the following. You somehow have to connect the error event probability to the cuts themselves. How do you make that connection? Okay, the way to make that connection is the following. So I have a source. Let's look at the dynamics of the problem. The source is sending out a vector xs over block time t. Relay receives something, sends something on. So this is the whole sequence of events. And the final destination receives yd. Okay? Now let's look at the error events. An error occurs when a different message transmits a different vector x prime s, has a different received signal and so forth. Error event occurs if you have two distinct messages which give rise to exactly the same received signal. Then you're screwed. Sorry. Then you're bad. Okay? Now, so let's look at that error event. So this is the overall error event. And now I want to break it down into a bunch of sub-events. And the trick is I can break it down, the sub-event, into according to the cuts. Okay? So let's think. Well, if you send the same, if you receive the same thing, then it must be that there are some nodes that has already received the same thing and therefore send the same thing. Remember, if you receive the same thing, then you send the same thing. Because you're using random coding, but the random coding is the same code for both of them. So you're sending the same thing, and you're sending the same thing here, and you're sending the same thing here, and then you propagate backwards. but eventually you will not be saying the same thing. So there must be a point in which the nodes stop making errors. So essentially these nodes are the ones which are confused. So not only the destination is confused, it brings together with it a bunch of friends and family, and they're all confused. So the blue guys are the ignorant people. The red guys are okay. I mean, the red guys can figure out the message. Okay? So now we have the red and the blue. And this precisely corresponds to a cut. Because the source is always correct, the destination, because of the error event, is wrong. So therefore, the cut is a legitimate cut. Okay? So therefore, I can break up my error event of sending M and incorrectly sending M prime. This is the pairwise error event. So this is classic information theory. You first analyze the pairwise error event, and then you do a union bound or some more sophisticated bound to get a tighter, to get an overall error probability. So I have a pairwise error probability, and the pairwise error probability is equal to the sum of a bunch of events where each event corresponds to a cut of omega and omega prime. In this cut, nodes in omega will distinguish as M and M prime, and nodes in omega complement do not distinguish, cannot distinguish. Okay, so now my job is to yes?
I have a question about the cuts. Is it possible if you're sending bits across the links and you have an error in one stage, then the bit gets flipped again in another stage? So basically you have an error and then another error that turns it back to be not an error. So if you had more stages in your network, can you look at the cut capacity? I mean, can you talk about the cut capacity?
No. Once you are in error, then you're always in error.
So you can't be in error and then the bit flips again and you're not?
No, because at this point, you are receiving now the same YA1 from the two distinct messages. So since you have a causality here, this guy can only act on the receive signal. So there's no way he can split out from that signal to two different XA1. So once you're in error, you are now confused. So there's no chance that you can sort of rebirth and give you a red. So the blue is always on one side and the red on the other side.
It's also because you don't have any noise in it.
That's right, there's no noise in the system. But the no noise in the system allows me to identify the error event as equivalent to this event, right? Yeah? Because in a deterministic channel, the only chance of making a mistake is when you receive exactly the same thing from two different messages. Okay, good. So now our problem boils down to computing this probability. Now, this probability, okay, corresponds to what? Now, so this probability corresponds to the fact that you are sending different things here, and you are receiving the same thing here. And remember that everything you send on the right-hand side is the same. Okay? Therefore, you can condition away the effect due to the transmitter signal on the right-hand side. That's exactly where the conditioning comes from. Okay? It's because these guys are wrong. These guys are all confused. They're saying the same thing already. So you can condition them away. So the condition is really that your x of omega on the left-hand side, the whole vector, is after going through this linear transformation across the cut, gives rise to something identical on the right-hand side. So this is this error event. Okay? And it's this error event. And the probability of this happening, or equivalently, is this error event. The probability of this happening, let's think about it, is x of omega and omega prime are two independent vectors because they're due to two different messages. Okay? Now I'm choosing each of these vectors at each relay node independent of each other. So now I'm computing this error probability over the random codes I used. So each of the component of h omega is completely independent of each other. Okay? And therefore, I'm just basically choosing a completely uniform vector in the input space. So as I go through the mapping, it will be uniform at the range of the transformation G. And so this event is the event that two uniform vectors are exactly equal to each other at the output. And since they're uniform, the probability of that is just equal to the size of that space. Okay? And the size of that space is precisely 2 to the power t, where t is a dimension, times the rank of this matrix. So this measures the number of possible values that the output can lie in. And 1 over that is the probability that two random uniform vectors agrees at exactly the same point. Okay? All right. So now we're done. Because now I'm going to do a union bound and say that the error probability is going to be the summation of this thing over all my pairs. And how many of them are there? There are essentially 2 to the minus TR of them. 2 to the TR of them. Because R is the rate that I want to send at. So as long as R is less than, so if you look at this term, what is this term dominated by? It's dominated by the minimum value of this, because it's, as a function of exponential t, the minimum of this is the one with the biggest exponent. And as long as the rate is less than the minimum of d, then I can choose t large enough to make this error probability arbitrarily small. This error probability is the error probability of the average performance over the random ensemble. And by average by a pigeonhole principle, there must exist a code with that average performance. Yeah?
Is t your time there?
Yeah, t is my time. T is my time. I am sending over blocks of length t here. Blocks of length t here. So that's the argument. And I must say, this is not like a breakthrough here. This argument is really following and understanding. 90% of the effort is understanding Raymond-Young's paper. And the other 10% is to make sure that I can apply to our problem. But our two problems actually share a very similar structure as in the linear mapping. So essentially, if you think about why network coding is so easy, not easy, but some of the fun, whoa. Mira is not here, I hope. Is because essentially, you don't have to worry about typical sequences, right? All sequences are typical because they're uniform on the space of interest. So everything becomes just a counting argument. In some sense, information theory is about reducing a complicated problem to a counting problem. But because everything is uniform here, we don't even have to do this reduction. Okay. And our model preserves that property. Our model preserves that property. Okay. So good. So union bound shows that this is achievable. And so this argument shows that we can achieve the minimum cut for stage network. So now we have to push ourselves to answering our audience requirement, which is to add this direct link, or in general now have an arbitrary network. So in an arbitrary network, things become a bit more complicated because now messages now mix in the network. Okay? So I cannot analyze this problem on a message by message basis through a block code. I got to worry about how these messages interact with each other. And our idea was the following. So to move to general network, our idea is to use this idea of time expansion. Okay? Now time expansion actually was also used in Raymond-Young's paper, if I remember correctly. At least it's in his textbook, which, by the way, is not easy to read either. But I love good stuff there. So I think they use time expansion to deal with cycles, yeah? We have to worry about time expansion even earlier on, even without cycles, because we have to worry about the interference. So let's do time expansion. What is time expansion? Okay. Time expansion means that, let's look at this 4-node network. So in this 4-node network, okay, is this a stage network?
No.
This is not a stage network, right? Because this is 1 hop, and this is 2 hop. Okay? So this is not a stage network. So what I'm going to do is I'm going to unfold this network. And what I do? First, I create a copy of S1, A1, B1, D1. So this is a copy of the 4 nodes. And I put them on one layer. Okay? And then I put another copy of that, and so forth. So this is like a bit like a trellis, And what do I mean by that? And then I'm going to connect these nodes up through this net in accordance with that network. So S1 goes to A2 through a link of capacity N1 bits. So this is the link. S1 goes to B2 interfering with A1 through a link N2, N3 bits. S1 goes to B1, A goes to B1, N2, N3 bits. So that goes here. So in other words, I'm reproducing the whole graph here. So this is describing, you will, over one frame of length t, the transmission of all these nodes, and this describes the receive signal at this time. Okay? All right. And this is time 3, and this is time 4. So now I've unfolded this graph. And now what I do is I put a gigantic source here. Okay? And I create copies of the source nodes such that at each time I'm injecting a message in here. So what I'm doing is essentially I'm describing the sequence of events where I have a bunch of messages, because now I cannot consider each message in isolation. I got to consider a whole block of messages, super message, going into the source node. Okay? Okay? But allowing myself to eject one block at a time in here. So this is, at the first time, I inject a block, and the signals get propagated here. And then next time, the source inject another block, the signal propagate down here, and so forth. And over a long super block of length t, this decoder is going to decode all the messages. Okay? So this, in some sense, describes a representation for an achievable strategy. The achievable strategy being that I do exactly the same as before, except that the source is going to do the encoding over this very long super block. Okay? So time is divided into very long time. And each of them is block length t. Okay? And the source is going to take my super message, randomly code it, and then at each time, it will send a block of length t into the network. And then the relay will do re-encoding based on what is received in a random way, exactly in a random way, like we described earlier, and send a signal forward. In the next time slot, the source will send the second block, this block being a coded block of the whole message. And then after a long time, kt, the destination will collect all the stuff that is received and do a super gigantic joint decoding of the whole thing. So this is how I deal with the inter-symbol interference, or inter-block interference, because the destination is doing joint decoding of the received signal of the whole thing. Yeah?
It's really effectively block Markov coding. You could do it without a full joint decoding, right? You could also kind of do a sliding window decoding.
Yes. But for proof of achievability, we are just thinking of this as a huge big block and do joint decoding. But that's right. You could probably do, yeah.
It's a block Markov. You're exactly using a block Markov technique where the delay, the number of block Markovity you have to have is the maximum delay through your network.
Yes.
So you could do it that way too.
Yeah, right. Yeah, but these issues about block Markov decoding really comes from the unequal path assumption. Yeah, unequal path assumption. Yeah, and so that's where that kind of issues appears. Yeah.
What do you mean here by infinite capacity? Because the maximum capacity here can be the size of the.
Yeah, you can do that too. But anything above that, actually, there's no use to do. So we just put infinity, but you can also put you can put Q. You can put Q here. Yeah.
As a comment to what you just said, makes sense, right? It's the unequal path mark. That's exactly why you use block Markov coding for the relay channel.
That's right.
Because you have that delay of one block.
Right. So in some sense, the relay channel is really not the simplest channel, if you think about it, because it has this unequal path length. Actually, that motivated why Brett Shine, I believe, and Gallagher to look at a diamond network, because in some sense, the diamond network doesn't have this problem. Yeah. So what we're doing here is essentially we're decoupling the problem into two parts. One, the equal path length part, which is dealing with the joint decoding, the typicality argument, and then this memory part, which we try to fix using some system theoretic way of thinking about it. Yeah. Yeah, so this is our famous, trellis, right? This is essentially a trellis now. So now what I'm doing is I am essentially limiting myself to a class of strategy here, where you allow super encoding of the whole big block here, and super decoding at D, or block Markov decoding. But within each relay, they're only doing re-encoding based on this small block of length T. Okay? So in fact, each relay actually receives information over multiple blocks, but they don't use that information. They only just look at the current block and then re-encode. Okay? So potentially I may be losing performance here. Right. Okay. But this allows me to model this whole problem as an equal path length or multi-stage or stage network. So this is a stage network now, because the path from the source to every node is an equal length. Okay? So now I can apply the analysis we did earlier for equal length stage network to this network, but now on the super messages level. And we can show that we can achieve the min cut of this network. Of course, you have to normalize by 1 over k to get the right bit rate, but essentially it's achieving 1 over k of the min cut of this time expand network. Okay, so this is based on our early result. However, we have an issue here, okay, which is min cut of this network normalized by k when k becomes large, because we can choose k to be arbitrarily large. Of course, for finite k, you'll probably lose some performance due to edge effect, but you can wash that out by making k large. But even by making k large, is this equal to the min cut of the original network? Okay, yes, the answer is yes. Good. Okay. So the issue here really is the following. Okay? If you look at this network, then this is an example cut of this network. Okay? Can anyone tell me, I claim that there is a cut on this network between across the source and destination, split the source and destination, which corresponds to this cut. Can anyone tell me which cut that is? Yes. Yes.
If you take any cut in this network, won't that cut be infinity?
Why infinity? Why? K is finite here, right?
So if you take any cut this way, it would encounter some infinities. Okay.
Yeah, so those cuts you don't care about, right? Because I'm interested only in min cut. Yeah, you can take some cuts are infinite, but they won't be binding performance. Yeah. Yes.
There are some links also like between S3 and S4 or S2 and S3 which you haven't in this figure, because all the information that S3 has, all the information that are in S4 will be
good. Yeah, in fact, if you think about, that's why I emphasized this network is not a representation of the original network. It's a representation of the specific achievable strategy that I'm using. Because what I'm saying is that essentially why focus on S, right? You can focus on A, for example. A3 is actually a copy of A2. So A3 knows everything that A2 has. So there should be, if you think about information flow, there should be a link going from here to here. But I am focusing on a specific class of achievable strategy where A2 just forget about all the past and just look at the current block, and so is A3. So therefore, this is a representation of the specific strategy I want to focus on only. Yes.
It seems to me that you replicate through this replication in order to obtain a multi-stage network at the end, in order to get needed simplification. Can't you introduce a virtual node in the network on the right, say between S and D and between A and D with infinite capacity, and then all the edges would be free?
But then you'll be increasing the capacity, right? So what do you propose? Put a node here?
Put a virtual node between S and D.
Between S and D.
S and D.
Okay.
Between S and D.
All right.
Let's say B prime.
Okay.
And there's an infinite capacity between B prime and D. And similarly,
B prime and B?
D.
Or between B prime and D?
No, B prime and B. Both in Bill. Both B as in Bill.
B as in Bill. And H as in Hillary. No. Okay. There's no H here. Or B as in Barack.
We also had yes we can this morning.
Yes, we can. Yesterday?
This morning.
This morning?
Yeah. Oh, forget it.
As in, yes, we can give the lecture if he's not coming, he's not showing up. Yeah. Yes, good.
Maybe do it quickly as it goes over the kind of between the third and fourth nodes, you just kind of swivel across horizontally. Yeah, exactly.
So this cut, okay, what is this cut doing? This cut is partitioning at every layer between the source A and node BD. SA on one side, BD on the other side. So the flow through this cut is correspond to this one, only that is replicate K times. But if you normalize by K, the cut value of this precisely corresponds to the cut value of this. Okay? So what I'm trying to say is that for every cut on the right-hand graph network, the original network, there's a cut in this graph. Okay? However, the unfortunate thing about this is that there are other cuts. So for example, this cut. Okay? So this cut has the property that the input, the left-hand side, so you look at all the edges which cross this cut and this stage, it is going from this set of nodes to this set of nodes. And these two are union, and these two union will get the whole set. But if you look at this cut, this is not so good. Because, for example, if you look at, what am I looking at? Yes. If you look at the edges flowing through this part, you have SAB on the left-hand side flowing to BD on the right-hand side. So B is actually repeated. So this does not correspond to the cut value of a cut in this original graph. So what happens is that the cuts, there are more of them. There are more cuts in time expanded graphs. So when you take the minimum of all the cuts, if this one is limiting your performance, is equal to the min cut, then it could be that the min cut on this network, on this representation, is actually less than the min cut of the original graph. And therefore, you cannot achieve the min cut of the original graph. Yes? Yes?
What should be the least number of layers in this graph?
Sorry?
What is the relationship of the least number of layers with the actual graph, in the layered graph?
What do you mean by the least number of layers?
What I'm saying is that if the number of layers, you have transformed the original graph into a layered graph.
Yes.
What I'm saying is, if there are not sufficient number of layers in the layered graph, you might not find the min cut in the original graph in the layered graph. So I was saying, is there some lower bound on the number of layers in the layered graph?
So by the way, the layers are not horizontal, yeah? These are not the layers. The vertical ones are the layered. Does that clarify the confusion?
I was talking about horizontal layers.
No. Horizontal is not a layer. The layers are the vertical. They're the layers. So, yeah. Okay, good. All right, good. Now, it turns out the answer is yes. So it turns out that these cuts, okay, these cuts actually cannot be a limiting cut. Cannot be a limiting cut. And actually, the proof is the following, okay, is a calculation. If you look at the cut value here, okay, and let me define this set at stage I to be above this graph, let's call it R1 complement. Below, let's call it R1. And here, let's call this R2, and this call it R2 complement. Then the cut values on each stage is the mutual information between the right and the left, right and the left. And this is just as we calculated earlier. It's just the entropy of the output given the input. Given the input. Is there a complement there?
Yeah,